The next one is number 6. In this one we have to prove lemma 661 and its corollaries, but without having direct sum. In place of direct sum we have to use ordinary sum, even if the sums involved are not direct sums. So let's recall the statement of lemma 661. We won't write the entire thing, of course, we are just going to see the main things. Lemma 661 was basically this. We have a vector space V over some field F, and V is finite dimensional, of course, and V is the direct sum of two subspaces V1 and V2. Also, there is an operator T on V such that V1 and V2 are invariant under T. This invariance lets us have operators on V1 and V2 themselves like this. If we restrict T on V1, then that restriction becomes an operator on V1. Let's call that T1. Similarly, restricting T on V2 gives us an operator on V2. Let's call that T2. We express this also by saying that T induces T1 on V1 and T induces T2 on V2. Let they have the respective minimal polynomials P1 of x and P2 of x over our underlying field F. So these are the ingredients, and that means the hypothesis. And the conclusion of the lemma is that then the minimal polynomial of T over F of the original operator over F is the least common multiple of P1 and P2. Let us give this a name also. It will then be easy to write. We have already proved this lemma. Now we are being asked to prove the same conclusion even when the sum is not direct. With this relaxation, can we still prove this? Yes, we can. In fact, that's what we have to do. So what can be better than simply going through the proof that we already have seen, and let us see how far we can have that same proof. If we can just simply take the original proof itself, that's it. That will be our thing. That will be our solution. Okay, so let's start the solution by recalling the proof of lemma 661. This is no longer 661, so let me put a star here. And we have to carefully see that nowhere we are going to use directness of the sum, because it's no longer direct. By the way, what is the difference between a direct sum and an ordinary sum? Both are sums, so in both of them, any vector in V is expressible as a vector in V1 plus a vector in V2. But when you have direct sum, that representation is unique. When you do not have direct sum, there is no guarantee of uniqueness. That's the difference. So how did we prove this? We started the proof by having an idea, by having an observation that we had in the beginning of the section itself. So let's just go back to that. Say you take any polynomial R of x. Just like V1 is invariant under T, it's a simple matter to see that V1 is also invariant under the operator R of t. And that is why, just like t induces an operator t1 on v1, R of t will also induce an operator on v1. The observation was this, that induced operator is nothing but R of t1. Okay, that was the observation with which we in fact started this section. Now, let's take a particular R. In place of R, we now take P of x. Actually, what is P of x? I did not write P of x here. P of x is the minimal polynomial of t. Q of x is the LCM of P1 and P2, and P of x is the minimal polynomial of t. The claim is that P of x is equal to Q of x. Now, if we take P of x in place of R of x, the same thing will happen. The operator that P of t will induce on V1 will be nothing but P of t1. But P being the minimal polynomial for t makes this the zero operator. Does that immediately imply that P of t1 will also be zero? Yes. Why? Because applying the operator P of t on any vector coming from V gives us the zero vector. That is why it's the zero operator. In particular, if that vector comes from V1, also we are going to get 0. In other words, if you take a V in V1 and apply P of t on V, because of this, you get the 0 vector in V. However, V is actually coming from V1. So, this is nothing but the restriction of P of t on V1. That, however, we have already seen is P of t1. So, V of P of t1 is equal to this, which is equal to 0. This means that P of t1 makes every vector from V1 vanish. And that is why P of t1 as an operator on V1 is the 0 operator on V1. Do you notice a very subtle thing? These two zeros are not the same thing. This is the 0 function from V into V, and this is the 0 function from V1 into V1. There is no need to see this, but sometimes seeing this kind of things, it just shows that we really know what we are doing. Okay. Alright, so we are now going to start the proof with this idea that P of t1 is equal to 0. We won't write all these things, of course. Instead, we simply write this. Since P of t equal to 0 induces P of t1 on V1, we have P of t1 equal to 0 as well. But when we say as well, just simply we may think that we are getting the same 0, but just now we saw that they are different zeros. We again get 0, that's what I mean. Alright, now forget about t1 and concentrate on the polynomial p itself. t1 is after all an operator just like t. Now p besides being means because it's the minimal polynomial of t, it's also the annihilating polynomial for t. If you substitute t in place of x, you get the 0 operator. The same thing is true for t1. So p becomes now an annihilating polynomial for t1 as well. However, then what can you say? Then the minimal polynomial for t1 has to divide this annihilating polynomial, and this fact comes from the basic properties of the Euclidean ring fx, and that's why we next write this. And you can in fact write like this, it will become more clear, since P1 of x is the minimal polynomial of T1, we have this thing, P1 of x divides P of x. Now whatever we did with V1 and T1, we can do an exactly similar thing with V2 and T2, and that way we will also get P2 of x divides P of x. But if P1 and P2 both divide P of x, then P becomes a common multiple. Okay, it's a multiple of both P1 and P2, and so by the definition of LCM, the LCM Q of x, which is the least common multiple, has to divide this common multiple P of x. So we get this divisibility relation. Okay. Now let us concentrate on Q of x. I mean, here we have Q of x, but let's now concentrate on Q of x itself. This is the other part of the proof. We are going to get the opposite divisibility relation as well. Now, since, okay, what is Q of x? Q of x is the least common multiple of P1 and P2. So after all, it's a common multiple of P1 and P2. P1 and P2 both divide Qx. So since P1 divides Q and P2 also divides Q, we have Qx equal to P1x times, say, alpha of x, and at the same time, because of this relation, this is also equal to P2 of x times, say, beta of x for some polynomials alpha and beta. What we now want to show is that if we consider the operator Q of t, replace x with t, then you get the operator Q of t, which is an operator on V, on our original space. We want to show that that operator is the zero operator. For that, we need to apply that operator on any vector coming from the original space V and have the 0 vector. So let's now take any vector. In fact, to make it even more clear, let me write what we want here. We now want to show that Q of t is the 0 operator. Let V in V be any vector. Now we are going to use the fact that V is the sum of V1 and V2, not direct sum, and we have to be careful that nowhere we accidentally use uniqueness or anything like that. Because V is just the sum of V1 and V2, then there exists a vector V1 in V1 and a vector V2 in V2 such that V is equal to V1 plus V2. Maybe there are other such vectors also, which when added give us V, because uniqueness is not guaranteed, but at least a pair of vectors exists. Okay, so we don't actually need uniqueness. Now next what we do, we apply Q of t separately on V1 and V2 and let's see what we get. V1 Q of t. There are two things we can write in place of Q of t. Let us use this one, P1 of t times alpha of t. V1 P1 of t times alpha of t. We don't really know what the operator alpha of t is, and we don't need to know. Why? Because P1 of t is equal to 0. I mean, P1 of t is the 0 operator. And that is why you get 0 times, well, I should not perhaps say 0 times, but on 0 we are applying alpha of t. And do not forget that multiplication means composition of functions. So we get 0. And on V2 also, if we apply Q of t, this time however we are going to use this. V2 T2 of t times beta of t. If you are keenly observing, you may have a slight confusion here. How is it that P1 of t is the 0 operator? Well, the thing here is that, you see, we are applying P1 of t on what? On V1. And where is V1 coming from? V1 is coming from V1. So in place of P1 of t, you actually are having the restriction of P1 of t on V1. Because V1 is invariant under t, so V1 is also invariant under P1 of t. However, then what is the restriction? The restriction actually is P1 of T1. Imagine this P1 in place of that R, that polynomial. So perhaps I should write one more line, then it will become clear. Otherwise, this looks like a gap. Because of this fact, you can actually write this as V1 P1 of T1 by again that first observation. But P1 is the minimal polynomial for T1. So P1 of T1 is the zero operator on the subspace V1. And that is how you get 0 here. And similarly, this is first it's P2 of T times beta of T, and then that's equal to, so similarly here we will have P2 of T2. Okay, that means applying Q of T on both V1 and V2 gives us 0. Thus, VQ of T is V1 plus V2 Q of T, since Q of T is after all a linear operator, so this is Q of T. So yes, that means Q of T is 0, because we have applied it on any vector in V and we have got the 0 vector. So Q of T is the 0 operator on V. That means Q becomes an annihilating polynomial for T. However, that implies that the minimal polynomial for T will have to divide Q. This implies, but the minimal polynomial for T is P of x. So this is the other divisibility relation. The other one we already saw before, that Q of x divides P of x. And now you use the fact that P of x being the minimal polynomial of some operator of T in fact is a monic polynomial. And what is Q of x? Q of x is the LCM of P1 and P2. They are also both monic. So LCM is also monic. So we write since and are both monic, those two divisibility relations imply that P of x is equal to Q of x. So that means we have the claim, we have proved the claim, and the proof went exactly like how it went in case of the original lemma 661. The uniqueness of that representation or the directness of the sum actually plays no role here. That's what we uncovered. So it may simply be a simple observation, but sometimes what happens now, when you go through a very, these things are not, I won't say easy or tough, but they need you to look at things carefully. Otherwise, you may inadvertently leave some crucial detail and think that something is true when it's actually not true. So after going through the proof carefully, we saw that directness of sum plays no role, and that's why we are able to have the exact same proof in this general case also. It's a different thing that we need directness for something else along the line, that we did some other things. We studied Jordan form and those things, but in general this result itself does not need directness. And what is the corollary? In the corollary, the number of subspaces is not necessarily 2. You have any number of subspaces. But now that we have this case where there are 2 subspaces, the corollary where also you do not have directness of sum is a simple induction proof. So that you can do, just like you have the original corollary. So that's just it. That's the 6th exercise. And let me end the video here itself. There are others also, we will do them one by one. And tomorrow, as usual, we have our analysis. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.